So let's see here. So we have 6x squared, 6x squared y plus 9y squared x equals -5. Now, if you potentially could write that in explicit form, yeah, feel free to do so. That is, if you could solve it for y, feel free. But there's no quick and easy way to solve that for y. To get y on one side and only x is on the other side. So since that's not the case, we're going to be stuck with implicit differentiation. So take the derivative with respect to x of the entire left-hand side. So 6x squared y plus 9y squared x. And the derivative of the entire right-hand side, which is not very much, but there it is. Now we have a property of derivatives that says if you have the sum of two derivatives, you can take the derivative individually and add the results. So we can say this is the derivative of 6x squared y plus the derivative, of course this is all with respect to x, of 9y squared x equals, let's go ahead and do that, that's just 0. The derivative of a constant is always 0, regardless if it's respect to whatever. Alright, so now this is going to require two product rules, because we have x squared times y and 9y squared times x. I could have been a little more astute here and factored out that 6. In fact, let me do that. Let me go ahead and say this is actually 6 times the derivative of x squared y, and this is actually 9 times the derivative of y squared x equals 0. I think that looks a little better. That's called the constant multiple rule. We can factor out a constant like so. Now, we have the product rule twice. Product rule here and a product rule here. So we have a y squared times x and x squared times y. So 6, now what does the product rule tell us? It tells us we have to take the derivative of the first function times the second function plus the derivative of the second function times the first function. But don't forget, we're multiplying that entire thing by 6. Then we have, let's do the same thing with the next one. 9 times the derivative of the first function, y squared, times the second function, x, plus the derivative of the second function, x, times the first function, y squared, close parentheses, all of that equals 0. Alright, now let's simplify all these little mini derivatives. That's a 6, stays there. That's just a derivative of x with respect to x, so nothing special, no special techniques required there, no chain rule. That's just 2x times y, so 2xy. Now, on the contrary, this right here, we have the derivative of y with respect to x. So the derivative of y is just 1, but we have to multiply by dy dx because this is a function of y, not x. So we say plus dy dx times x squared, so x squared dy over dx plus 9. Okay, a similar thing happens here. That's a y squared. So the derivative of y squared with respect to x is 2y. But we have to multiply, because the chain rule is going on in the background. It's 2y times the derivative of y with respect to x. That is dy dx. But there's an x right there, so I'll write x first, then dy dx. Plus, okay, that derivative is just 1, so 1 times y squared is y squared equals 0. Now let me recap. What do I mean by like dy dx chain rule? Let's just take the derivative of y squared with respect to x. Let's take that for example. We could say that is actually the composition of the function f of x equals x squared and g of x equals y. That is, if you look at f composed with g, this is your outside function, this is your inside function, And f composed with g like this is actually equal to y squared, which is what we have right there. So what does the chain rule say the method for taking derivatives is? It says you take the derivative of your outside function, so that's f prime of x equals 2x. So you take the derivative of your outside function, but you evaluate it at your inside function. So I would write 2x, but instead of an x, I'm going to write my inside function, which is y. And then I multiply by the derivative of my inside function. So I multiply by g prime. But g prime is just the derivative of y with respect to x, otherwise known as dy dx. So times dy dx. And that is exactly what I have there. Except we had to multiply by x too, since it was right there. Now, the process, we had this four-step process. The first step was to take the derivative of both sides. So we have done that now. So that's like step one so far. That's step one. Step two is to isolate the dy dx terms on the left-hand side. So I need to distribute here. So I can say let's see, I can say 12xy plus 6x squared dy dx plus, let's see, that's 18 yx times dy dx plus 9y squared equals 0. So that's step two there. So step two is not too bad. Step three is to, actually that's not step two. I'm not done with step two. Step two is to do what I just did, but also to get all of the dy dx terms on the same side. That is the left-hand side. So I'm going to take, I have them on the left-hand side already, but I'm going to take everything else to the right-hand side. So I have 6x squared dy dx plus 18 x, or yx, xy, that's fine, dy dx equals, I'm going to take everything else to the other side. So that's going to be a negative 9y squared minus 12xy. So I have my dy dx term on the left, everything else on the right. That is step two. Now, step three is to factor out the dy dx's. So let's factor out that left-hand side. I'm only really concerned about the dy dx's. I might be able to simplify later on, but for now, I want to factor out only dy dx. That leaves me with 6x squared plus 18xy equals, okay, the right-hand side is unchanged for the time being. And now to solve for dy dx, so that's step three done. Step four is just to solve for dy dx, which means I just need to divide both sides by this entire set of parentheses and say that dy over dx equals, okay, it's my current right-hand side, negative 9y squared minus 12xy divided by this factor here, 6x squared plus 18xy. Now, of course, I would need to simplify in whatever capacity I can. I think that I could factor out a 3 out of the top and a 3 out of the bottom. So that would leave me, let's see here, with a negative, a negative 3y squared minus 4xy over x squared plus 6xy. I just divided everything by 3. It's like reducing, 2/10 to 1/5. Okay, we just divided the top, everything by 3 on the top and bottom. So we divided that by 3, that by 3, that by 3, and got 2x squared, and that by 3. Anything else we can do? We could factor an x out of the bottom, but we can't really cancel it off or anything. We could factor out a y out of the top. Yeah, I guess we could do that if we really wanted to. We could factor like a negative y out of the top, and that would leave us with 3y plus 4x divided by, if we factored out, say, an x on the bottom, we could write that as 2x plus 6y. Is that really necessary? I don't know. But it makes it maybe look a little bit better. All right, so that's done. There is the derivative. Simplify as much as possible. The steps are take the derivative of both sides. Get your dy dx's on one side, everything else on the other side. Solve for dy dx. Factor, then solve for dy dx. Okay? Now, let's look at a trig one. All right, so this is a trig example I thought I'd work out as well. So this is sine pi x plus cosine pi y, all raised to the 7th power equals 18. So there's our original function, but let me give myself a little more room here so I don't have to copy that exact same thing down again. So I say like equals 18. Now, the reason I gave myself some room is because I want to take the derivative. I mean, that's the immediate thing to do, is take the derivative of both sides, because, there's not a good way to solve for y. I mean, you could, talk about taking the 7th root of both sides, then using, arc cosine and stuff. It's going to be, you don't want to deal with that. Let's just take the implicit derivative. That is, take the derivative of both sides. That's why I gave myself some room there. Take the derivative of both sides of that equation. Now, see, we have a 7th power over there. Let's think chain rule. Okay, we have a big a sum of two functions here raised to a power. Let's think chain rule. Now, let's start easy, though. What's the derivative of 18? Well, with respect to x, sure. With respect to y, whatever. Doesn't really matter. We're doing with respect to x. It's 0. Derivative of a constant is 0. Now, let's think about this left-hand side derivative. What does the chain rule say? The chain rule says, okay, what's our outside function? Our outside function over here, f of x equals x to the 7th. What's our inside function? Our inside function, we'll call it g. That is, let's see, it's sine pi x plus cosine pi y. So if we think about the left-hand side being f composed with g, with these two functions, the chain rule, I think, comes pretty obvious. The chain rule says it says take the derivative of the outside function. F is the outside function. So what's the derivative of x to the 7th? It's 7x to the 6th. But we're going to evaluate. Oh, I need a lot more room. Let me reassess how much room I need here. Let's say 7 times x to the 6th. But we evaluate that derivative of our outside function at our inside function. So we evaluated it at sine pi x plus cosine pi y. So there is the derivative of our outside function, 7x to the 6th power, evaluated at our inside function. Outside function, inside function. But the chain rule says, wait, you're not done yet. You have to multiply by the derivative of your inside function, which we know is sine pi x plus cosine pi y. So we have to multiply by that. Okay, so now we're done with this, this most left-hand part here. We have to figure out this right-hand part right here. So let's rewrite the 7 times sine pi x plus cosine pi y to the 6th power. Now, what is this? It's sine pi x. Now, that's actually another chain rule. Because you have sine x, that's the easy derivative, that's just cosine x. If you, along with that x, then you have to use the chain rule. So that right there is the, so we need to take the derivative of sine x. So let's just go ahead and use the chain rule. The chain rule says, okay, let's define here. If we say f of x is sine x, then g of x would be pi x. So outside function, inside function. So we take the derivative of our outside function is cosine of x, but we evaluate it at our inside function, which is pi x, but we have to multiply by the derivative of our inside function. So what's the derivative of g of x? Well, it's just pi. Okay, that's the first half, plus, let's do the same thing here. The derivative, now the derivative of, well, first of all, sorry, let's look at outside, inside. The outside function, f of x, is cosine x, and the inside function, we'll call it g, is pi y. So we take the derivative of our outside function, which is negative sine, we'll say negative sine x, but we evaluate it at our inside function, which is pi y. But then we have to multiply by the derivative of our inside function. So what's the derivative of pi y? Well, it's pi times 1 times the derivative of y, because we're taking the derivative of y with respect to x. So dy dx. Okay. Equals 0. Sorry, almost left that off. So we need to isolate that dy dx. Okay. So let's see here. We have this thing right here. This is a single item right here. That's a 7 times something to the 6th power. Times this, times this. So we have just a big distributive property to worry about. So it's 7 times sine pi x plus cosine pi y to the 6th power times this, which is cosine pi x. Oh, I'm going to write that pi in front. That'll look better. So pi cosine pi x. So we have that minus this, which is 7 sine pi x plus cosine pi y to the 6th power times, let's see, yikes, we have a pi times a sine of pi y times a dy dx, and I'm running out of room. So I'm going to erase a little bit. Equals 0. Let's just double check there. That was just a big nasty distributive property. I know it started with a D. So let's see here. 7 times this, or excuse me, 7 times this. Yeah, this whole thing, that's just like a single item there. And I multiply by cosine pi x pi. Then I took that entire thing, 7 sine pi x plus cosine pi y to the 6th power, times this thing, which is a negative sign out front, a pi, a sine pi y, dy dx. Yes. So what I'm going to do is get that by itself. So, I mean, I can think about, I'm going to take it to the right-hand side just because that'll make it positive. We always say left-hand side, but it doesn't matter as long as it's on a side by itself. So let's say that 7 times sine pi x plus cosine pi y raised to the 6th power times pi cosine pi x equals negative 7 sine pi x cosine pi y. Let's see, to the 6th power times pi times sine of pi y times dy over dx. Now, there's nothing to factor there. I just need to divide both sides by that to get dy dx. So we're going to have 7 times sine pi x plus cosine pi y to the 6th power times pi cosine pi x divided by, there's a negative, so a negative sign, 7 sine pi x plus cosine pi y to the 6th power times pi times sine pi y equals dy dx. What do you notice about a whole bunch of stuff there? That's the same on the top and the bottom. That's the same on the top and the bottom. That's the same on the top and the bottom. Cosine pi x over sine pi y. You almost think like you could write that as, what's cosine over sine? That's cotangent. But you can't because the arguments aren't the same. So we're left with negative cosine pi x over sine pi y equals dy dx. Sure was a whole lot of nonsense to get to that tiny answer there. But there we are. So step 1 is to take the derivative of both sides. So we essentially were done with derivatives at this point. So there was essentially step 1. Step 2 was to isolate your dy dx, which was essentially this step. And then we didn't really have to factor, so we kind of like skipped out on the 3rd step. So we go straight to the 4th step, which is this right here. So 1, 2, no need to factor because we only had one dy dx term, so we didn't have to factor. Skip step 3. Step 4 is to solve for dy dx. Let's say step 5 is that simplification that usually is the hardest part. Wasn't too bad this time. So there we are. So the derivative of this pretty crazy function up here, the derivative ends up being just negative cosine pi x over sine pi y. So it turns out a pretty simple solution. In the very end, I wouldn't have imagined the derivative was this refined when you're looking at that originally. So, hope it's been helpful. Always feel free to ask for help if you are having issues with your homework or you just want to see some examples worked out.